Okay, thank you very much for the very nice introduction and the invitation to speak here. So my original title was Machine Learning for Risk Assessment of Transcatheter Aortic Valve Replacement, but getting more into the topic, I had to change that title to the collaborative approaches for the AI-based integration of image data in decision support, because that's actually what should enable a better risk assessment and, in addition, better decision making in this field. Sorry. So, coming first to the risk assessment task. So bringing that in the context of clinical decision support systems, clinical decision support systems are defined as active knowledge systems that consider existing patient data. And that means the integration of medical knowledge, databases, patient data, and an inference engine. And then they are supposed to give case-specific advice. When we look at the typical risk scoring systems we have for TAVR, those systems give you a score. So scores have been traditionally used for a long time, and they are typically based on the analysis of available data at one certain point in time, and then a statistical model is derived, and that is applied based on the available patient data. So when those risk scores are used for decision making, they typically appear in the decision trees suggested by the clinical guidelines. And they are very frequently used, but there are several studies complaining about the lack of performance of these models in actual applications to the specific data in a certain site. So when we, from the computer side, look at the topic, then we typically, as engineers, do not think in we want to recognize a risk, but we want to support decision-making by giving an advice or making a suggestion for the best solution for the problem, actually. So maybe here one problem could be that the data that is used for those risk scores, because it depends on the available data in the databases used to develop the score, is too limited. And in clinical practice, image data is used in addition to plan the optimal intervention. So why not consider the image data in actually giving the advice? So when we want to do that and use machine learning for that, we typically need representative image data. We heard that in the previous talk also. And if we want to have a representative model which is widely available, that should be multicentric data. So that is the first task for us as engineers, make these multicentric learning projects possible. Then, of course, when looking at the way image data is currently used in decision support, there are very simple parameters which are derived from the image data. So the next task for us is to find out what is the relevant information in these data sets and how could that be integrated. So I talked about the need for collaborative approaches already, and when we think about how to work with the multicentric data, we face a lot of problems with data security, data sharing, and so on. And luckily, there are other countries where that is a bit easier. And at the moment, the whole image processing community benefits a lot from a very recent approach that has been published by the University Hospital of Basel, where they made optimal use of what the community from the image processing side already provided. There are public data sets, there are challenges, and there are machine learning models which are publicly available for, so to say, small problems. So, for example, for the segmentation of the spine or for the segmentation of the left heart chamber, and those data sets are small. But what the Basel people did was taking these approaches, which work, but maybe not too well on a wide range of data, and apply that to the available data sets they had in their PACS system. And they got full consent from their patients, so they could use in an active learning approach these models, improve them, adapt them to make them more performant on a wide range of segmentation tasks. So we as a community now benefit from, on the one hand, the annotated image data they made publicly available, on the other hand, from the models which can directly be applied. And when we go back to our task, of course, for making image data integratable in the risk assessment and decision support task, we have to provide a preprocessing. So here you see how that approach has been integrated in our development platform, Mewis Lab, and what the result is if we apply that to one typical data set we have in clinical practice. So you see there is a lot of structures have been segmented, and the result looks promising, but actually it's very inaccurate. But it is a basis can be a basis for our next steps. So we still have our tool case for standard image processing, which enables us to derive information which could be relevant for decision support, such as what is the course of the aorta, what geometric features do we have there, and where is the actual diameter, and we can improve these segmentations we get from the simple approach from this total segment data from Basel with our tools and expert input, and thereby improve the annotations and enable a further training of that approach to make it better for the application we have. Then once we can extract the important information for what we want to address, namely the aorta, we can then extract features. So machine learning typically is based on features. Those features can be learned by a neural network, or those features can be provided by us. And those features are descriptors of what we see in the image. So this can be descriptors of the shape. So what is the course of the aorta? What does the diameter look like? And what are certain angles between neighboring structures, such as we see here in the example of the angulation of the valve plane in relation to the LVOT and the aorta. And so we want to take those features to find out how we can predict difficult cases, or how we could predict personal outcomes for a certain device that could be implemented. And now we come to the next way of collaboration. So we work on that topic in the FLOTO project. The FLOTO project is funded by the German Center of Cardiovascular Research, and it supports building up an infrastructure which enables to integrate different clinical sites for joint machine learning tasks. So at the moment, we have a bunch of clinical sites which contribute here with their data and their knowledge, and they are all integrated via a system of interconnected computers that enable the processing of the data locally. So the idea here is, because we have the strong regulatory requirements in Germany which make it very difficult to exchange data, we want to connect the sites and let the algorithm travel to the data instead of doing it the other way around. So we have to use a lot of software infrastructure. We have to use security layers here. And the idea is to have a server in a hospital the hospital is a data owner, and we can start training there. And then from that hospital, we transfer only information about what the network has learned, so the weights of the neural network. And then at our central node, we can combine that weight information and provide the fully trained network which considers the data from the different sites for the final solution. The data scientists then have to take care of how to design the algorithm and the algorithm training in that environment. So a bit about the concepts of training in such an environment. Of course, there are several ways to organize that, and actually the results are unfortunately dependent on in what order we process data or how we bring together the weights. So we could have a distributed global model. So then we send our model to all sites in parallel. The models are trained, we get back the weights, and we provide a weighted sum of what has been learned in those hospitals for the final model. That's the aggregation idea. We could also say we have a more decentralized approach, and then say we go for approaches such as transfer learning. So train on one side, let the trained model travel to the next site, do a retraining on the available data there, and then our final result depends on how we organize the traveling, but still we can consider multicentric data, and we can use this infrastructure we're building up also in such a way, for example, to enable bicentric collaborations. So what we are doing now with that infrastructure, which is also still work in progress, but we're looking forward very much to having all computers installed by November. We want to support the optimal device suggestion. And what we collect in Flotus, so every hospital provides to the server anonymized image data, information about the implanted device for that case, and certain outcome information. And then what we're working with here is, on the one hand, first, as I showed, the analysis of the aortic root, so that we can reduce the analysis for the optimal fitting to the place where the device is delivered. Then a solution for the assessment of the access path. So as I showed, we also extract the whole aorta, and we can analyze diameter calcification, whatever might be of interest here. Then the device selection, and finally, of course, the risk assessment. So the preliminary results are concerned with the data we have at the DHZB, and which we could pre-process in a fast way, so to say. And for that, you see the publication provided by Nina Krüger. And we are not totally happy with the performance of the model yet, but it's increasing with the amount of data we get, and we get relatively accurate predictions of the aortic diameters now. So the next thing to consider, because I mean, typically what one wants to achieve here is optimize the flow. So one important question here is, couldn't we better support decision-making by considering also flow profiles, first in the assessment of aortic regurgitation and stenosis, and second in the assessment of the outcome of an intervention. And here's an example from some publication from 2018, which nicely shows how the profiles can differ between controls and patients. And one question is here, could we reproducibly extract relevant information to use that in assessment and also in machine learning? So what we have to do there when looking at the data, of course, we have to provide a 3D segmentation, and we have to provide a segmentation over time. And when we want to compare the assessment between different patients, we have to go for a concept which is standardized, and that's one of the problems in the assessment of flow data, that there are no standards or conventions yet. And here we also have within the German Center for Cardiovascular Research a collaboration between several sites who contribute data here to train models which do the extraction of the 3D models and also the contours in the cross sections, and thereby enable a more reproducible, more standardized assessment in all centers. So then the question is, and this is actually really ongoing research now, how do we reproducibly and easily assess the flow profiles? So we saw the flow profiles might matter, but we're dealing with vector information here, and it's time-resolved vector information. So the nice thing is that we can consider, on the one hand, the flow direction. We can consider shape, because we also have the 3D anatomy, and we have that over time, so we can also consider the motion. And, of course, the velocity distribution within the flow profile. So looking, for example, at the direction problem, when we compare the flow direction and how it changes over time via analyzing the wall parallelity of the flow vectors in volunteers and diseased persons, we see very clear differences here. So especially in regarding the change over the heart cycle. Also interesting, and that fits well with what Boris Schmidt was showing, we see very different patterns in the motion and also in the changes in the diameter in the aorta between healthy and diseased patients, also suggesting that that might matter also for planning and decision making. And of course, if we have a jet, we have a totally different velocity distribution, and that can be well described by the skewness of the velocity histogram. So, but you see, we have a lot of construction sites, and to make our AI models applicable to our problems, we have to know how to formulate the problems in such a way that they can be solved by the AI. And one has to be very careful when formulating these tasks, because if you ask the wrong question, you get a useless answer. Okay, thank you very much.
Any questions from the audience? Anja, may I have a short question? You pointed out the difficulty of pre-processing the images. How complicated will it be in the future in Germany with all the lack of physicians, of technicians, and so on? Who is doing this job?
Yeah, so actually that's a job for the AI. So typically, machine learning, many of the solutions are not too intelligent, but they can perform simple, well-defined tasks if they have seen enough examples. So we're working towards, and there these multicentric approaches are very important so that we get representative data, and with the representative data, I hope we can automatize this pre-processing, and then we achieve also a higher standardization and reproducibility over sites.
Thank you very much. Felix? No? Yes? Okay.
I always have questions. If I understood you right, in your aggregation model and for learning and training the network, you transport the delta. That means the difference of that what you already know from that what has been observed newly. That's an interesting aspect, and I want to ask you whether there might be a, let me say, an artificial bias or some bias what you cannot overlook, because the delta or the change of that, what happens, does not happen for its own. It's happening in a global environment, in a patient. How can you make sure that this is not overestimating the change or underestimating a change?
We can't. So actually, so the software deals with what is available to see, and in the end, it interprets the data in the context that has been learned. And that's the strength of the humans compared to the AI. You typically have more context from experience, context from information that has not been fed to the AI, and that's what I mentioned. So for AI is good for simple, well-defined tasks, so you have to clearly also know where the boundaries are and the limitations. And so that's why these active learning approaches are so attractive. It's very difficult regarding the regulations, because if something is adaptive, it has to be validated again and again all the time. But in these approaches, the AI can learn from the user input and especially process and weight inputs that differs from what the AI would have expected.